전부였던 동안 숨이 벅차도록 달려왔잖아. Never say time's up. 경계의 끝자락 내 끝은 아니니까. 울타리 밖에 일렁이는 무언가 그 아무도 모르는 별일지 몰라. I wanna be there. I'm gonna be there. 벅찬 마음으로 이 궤도를 벗어나. Let's go. 새로운 길에 탐험가 Beyond the road. 껍질을 깨뜨려버리자. 두려움은 이제 꺼도 오로지 나를 믿어. 지금이 바로 time to fly. 두 눈앞에 끝사뿐 넘어가. 한계밖에 trip 자리 찾아라. 너의 심장에 쉼없이 피는 꿈. 무모하대도 믿어 난. 누구도 본 적 없는 낯선 우주 속에 겁없이 뛰어들어 fall, fall. 답답한 가슴 안에 불꽃을 피워낼래. Shine and bright. 거쳐 듯이 반짝이던 무언가 꼭 달릴수록 멀어져도 난 좋아. I'll never never give up. I'm getting better. 여정은 이미 시작된 지 오래야. Let's go. 끝이라 생각한 순간 Beyond the road. 너는 세상이란 감싸나. 때로는 느릴 때도 가끔은 지친데도 멈추지 않고 let me fly. 두 눈앞에 끝사뿐 넘어가. 한계밖에 trip 자리 찾아라. 너의 심장에 쉼없이 피는 꿈. 무모하대도 믿어 난. 누가 뭐래도 믿어 난. 다치고 망가져 버거워진 한계. 숨 한 번 고르고 이어가면 okay. 그럼 너와 세상을 내 품에 안을래. 두 눈앞에 끝사뿐 넘어가. 한계밖에 trip 자리 찾아라. 너의 심장에 쉼없이 피는 꿈. 무모하대도 믿어 난. 나의 여정을 믿어 난.
It's dark in here. Let me see if I can find something to turn on. If I can find the damp window. Sorry, I've made a complete mess of everything. Oh, there it is. Yes, right. Right. Welcome to... ooh, sorry, something exciting happened in my output capture. I think I'm looping back something I shouldn't be. Let's just turn off that. Welcome to TIS-100, which is the game that kind of comes before Shenzhen.io, like a couple of decades before in storyline time, if not quite in real time. So yes, there is some backstory. As you can see, I'm being encouraged to read the manual, which I'm not going to do. Apparently I sounded like I was in the biscuit tin before I fiddled the audio, which might be appropriate. There is some backstory though, which is that the player's uncle Randy has left the player, him, her, it, they, that's not right, is it? Them an entire garage full of old computers. But
wait, I know one. You've got to find the map of Paris.
more or less. And this, but there's one particularly interesting one which he was working on when he disappeared, which is labelled TIS-100. And you do have a manual for this, but as with Shenzhen IO, trying to work out how I stream the manual is just going to be painful. So possibly I'm going to need to open the manual to remember how it works, or possibly I'm going to be able to do this entirely from memory, because this is actually the third time I've played TIS-100. I did it once quite some time ago on my old computer, once on this one just before I started Shenzhen IO, and this time. But I've reset everything to an empty save file, and so we'll see how it goes. But yes, I will probably need the manual, because, well, you may have noticed the copyright date in the startup screen says that this machine was built sometime in the 1970s. It does seem a bit advanced for the 1970s, but that's kind of part of the plot. Actually, if I hit the view the TIS-100 manual button, thank you. If I hit the TIS-100 manual button, I get told where to load the manual from. I could work most of that out for myself. Right, so people in the house can see the manual, which is a PDF, which has a note attached to it from Aunt Doris, which says, "We are all still in shock here from Uncle Randy's sudden passing. While we wait on word from the examiner about the cause," okay, maybe his body was found, "we are coping as best we can. I've been occupying myself sorting through his things, especially his computers. Of course, I took one look in the garage and it all looks like a bunch of junk to me. I'll send some pictures when I get a chance. For now, this is the machine that was set up on his workbench when he died. Maybe you'll be able to figure out what he was doing with it." He would have liked to know someone was going to finish his work. So yes, the tessellated intelligence system is a massively parallel computer architecture comprised of non-uniformly connected heterogeneous nodes.
This does sound like something that someone in the computer lab in the 1970s would totally have tried to build if they could.
I mean, there is a definite transputer feel to all this.
This is massively parallel in the sense that there are 25 processors.
Give or take. I can't remember if it's actually 25. This is the.
I mean, I think more than those these days can count as only normally parallel.
Yes. 1970s. So yes, there is a manual, and I'm not going to read the whole thing out. But it tells you roughly how it's organised, a few interesting things. Unauthorised requests for copies of documentation describing this node are reported to the State Security Bureau as required by law. But we start with segment 00150. So the general problem is... Jacob says, possibly I should have found the manual on some dial-up BBS, but I don't think I have the upload-download ratio for that. Have you seen some of Zachtronics' more recent things, which is indeed a 1990s BBS simulator? Kind of. In a very alt 1990s. Anyway, so we have... So the system failed its power on self-test because a bunch of its test routines were corrupted, and so we have to write new test routines for it. So here is our somewhat broken set of available nodes for building a test routine in. We have a button labelled debug on this broken node over here. Sadly, of course, no one other than us now gets that noise because I've turned off audio output captures because it does weird things. Oh well. Thank you. Verity imitates the noise of the computer. So compute node diagnostic microcode dump. Clearly this is Randy taking notes. Oh, Seb apparently heard a noise. Oh, you probably get the noise from our television coming through the microphone, which is going to be good enough for these random parping noises rather than the actual music.
Yes, that was the thing that killed my attempts to stream StarCraft 2 originally. That the feedback round the microphone to speakers loop made it impossible for me to turn the game sound down to the point where people could hear my voice.
Yeah.
I eventually had to give up completely on the speakers and go to headset.
So yes, he has this object that he got for $200 and he's trying to work out what the hell it is. And since he can't find a pen, he's just making notes in random bits of unused memory in the in the system ROM or something. So, well, we seem to have a program here that looks like it will work. Yes, Randy has been writing code in the notes in the microcode space. Curiously, this has not made it work any worse, largely because all sorts of things are kind of broken anyway. So, but we seem to have a program here that, that will copy data from up to down in each of these, and all we have to do is read data from in and write to out. And so, if we click run, we will find that, right, yes, that works, but we also have to read from in.a and write to out.b. And we don't have any code in any of the processors over here, but happily that shouldn't be too hard to do, because, well, we need to route around that broken processor. But other than that, it should be fairly easy. And like in Shenzhen IO, we have a tiny processors with a small number of instructions with 2 registers. So it's the Ponzi processor in Shenzhen IO, and synchronous links between them. Possibly, if I said B, I probably meant X. It doesn't really matter because we never talk about those. We talk about up, down, left, and right. So, by writing a bunch of programs, each of which just reads data from one of its processor's ports and writes to a different port, we can go from up to left here, from right to down here, from up to down here, from up to right here, from left to down here. Shovels data all the way through. So now, both halves of the program work, and much as in Shenzhen IO, we have a button that says, run this test. And we have histograms telling us how we did relative to everyone else, and everyone writes the same program for the first test. And so now we have access to segment 10981, signal amplifier.
So when I said there were 25 processors, I thought these were they, but actually these are the levels. So
yes.
There's fewer processors.
So yes, you have at most 12 processors.
Yes. Oh, that's definitely not massively parallel.
So, read a value from in.a, double the value, write the value to out.a. We've got quite a lot of space to do this. I suspect most of these processes are just going to be shoveling data from one place to another. Meanwhile, what's our little bit of story? Continues to baffle. Chatted with Bernie at IBM, and he says it sounds like something they'd come up with in the USSR. Then why is the manual in English? So, as I recall, we do at least have like an add instruction, don't we?
So they mentioned the USSR because there's a back register.
Thank you, Simon. Yes, right. We have add. So, as with the Shenzhen IO processors, add operates on the accumulator. So it adds something to the accumulator and stores the result in the accumulator. So if we want to double something, that's fairly simple. I think I don't actually own any things with transputers in anymore. I think I gave all of those away. I think Ian knows a better answer to what's a transputer than I do. They're is it like a computer but sideways? They were a microprocessor invented by Inmos that notably had, I think, on each one 4 very fast synchronous communications ports for talking to other transputers, with the idea that you would assemble them in a mesh very like this one, and then you could write clever parallel programs that worked by message passing between these lots of little processors. And the SJ Research Nexus system was built based on them, and I did, and when I discovered that, I understood why some of its bizarre design decisions were the way they were. Like, why did the Nexus routers, some bit of Nexus kit allow you to plug into one port on your Nexus and get 3 ports on the other side of it? And of course that's because it's a single transputer with 1 link that goes upstream and 3 links that go downstream, because Nexus actually just used the transputer links. Jacob is objecting that this is not actually a proper text mode display, that the numbers are actually aligned on half character increments. Yes, well, sorry. So if we're going to double a number, then we probably just want to move up ac, more add ac, move ac down, move up, down. We probably need commas in this processor, don't we? Move up, right, move left, down. I'm wondering now if there's a way you can make one that has a shorter runtime by parallelizing the making copies of ACK and the adding. Because, like, at the moment we have a three instruction cycle time. No, we'd still have to send it two times anyway. Yes, ACK is the accumulator. It's the register you can do arithmetic on. So if you want to add anything, one of the inputs has to be the accumulator and the output has to be the accumulator. Right. So, yes, some people manage to do that less efficiently than that. Segment 20176, differential converter. And this is the point at which we can see the statistics start to get divergent, as not everyone has the same solution to this one. Even most people don't have the same solution to this one. So,
most people don't have the same solutions themselves.
So, read values from in.a and in.b at the top. Write in.a minus in.b to out.p. Write in.b minus in.a to out.n. And a piece of plot. Interesting. It looks like there's some kind of static memory in this thing, encoded something or other.
When you say it looks like, it looks scribbly.
Yes, okay, it looks scribbly. I think the microcode may not be in the best of... Microcode memory is, well, not very reliable, hence the problem with half of the... with some of the test segments being broken. Which is why we're having to write some code to get it to pass its self-tests, apparently. So, So we need, obviously we're going to need to read the data in. Like, it feels like we've got rather too many processors here for the job at hand. So we want to calculate A minus B. So the obvious thing is to do something like, I feel, is simply send B to the left processor. Then we can go sub right. Now we've got A minus B here. And then we need to do B minus A, and that's just minus what we've already got in this processor. So surely we can go... Oh, it looks like it might not need the commas. So the way that the timing works is that the links are like XBus in Shenzhen IO. That so if you attempt to read anything, your processor will stall until something on the other end writes to it. And similarly, if you attempt to write something, your processor will stall until something on the other end of the link attempts to read from it. Which I vaguely recall is actually how transmuter links behave. And so you can mostly ignore the timing until you accidentally make a deadlock. Things get a bit more entertaining with later things where they start introducing stacked memory nodes which have weirder behaviour. So we could now just go mov naught ac sub left. And I think that'll do it, because that will effect. Do we have a negate instruction actually? Oh, we have a neg instruction. That's a little bit simpler then. Well, I mean, I say that it's not. It's precisely the same number of instructions. Mov naught ac sub left or mov left ac neg.
And you apparently don't get to do neg by mul minus 1, which you could do in...
Because we don't have a multiplier.
Indeed.
Yes, that was why I was expecting a neg instruction in Shenzhen IO and then didn't have it, and was like, ugh, how do I do this? Oh, right, we have multiplication. So now, and we can single step things to show how the timing works. So like, the right processor then stalled for one instruction waiting for that sub to happen. So actually there is a difference in doing the instructions the other way round. It would make the two processors line up, timings line up better. So yes, the left processor does the subtraction, sends the answer down in order to get it to out.p, and sends it right in order to get it negated. But actually that's a really silly approach, isn't it? We can do that much more prettily. Because instead we could... Oh no... Well, we could have this processor do the sending a copy to the right, because it's got spare CPU cycles. So it could go mov up, ac, mov ac right, mov ac down, and then we can blank that processor and move all of that code. I mean, you can tell it's not really a 1970s processor computer. It's got copy and paste. And remove that line.
Maybe you're very sensibly working on all this through an emulator.
But well, I mean, yes, in reality I am, but obviously not in the in story because this device is some weird thing we don't really understand.
The aperture science thing, we don't know what it does.
Yes. I mean, we don't think it was built by Aperture Science, but...
But there is plot yet to be revealed, so who knows?
I'm still here.
And I've screwed that up because that's still copying things to the right. Sorry, I apologise, Claire, for the fact that I'm redesigning the programme while you're trying to understand it. Right. So, right, I will attempt to explain. The box below in .b can read from, hang on, let me stop the program, can read from any of the 4 directions. It has 4 arrows that point in towards it. Which one it reads from depends on the instruction you write. So it only has one instruction. Its one instruction is mov up left. So what it does repeatedly is it reads from up, that is the input just north of it, and I've just realised you probably can't see my mouse pointer because I think I turned that off for Dwarf Fortress. And it writes to left the... I can tell whether you can see my mouse pointer by doing this. Left... No, you can't. Cell the processor to the left of it, and as in Shenzhen IO, as soon as it reaches the end of its instruction, it goes back to the beginning. Wonder if that button will help. Ooh, that's the wrong that's the wrong window. Go back to the correct window. Thank you. Right there. Now you have a mouse pointer. We apologise for the brief burst of Emacs. Happily, my Emacs doesn't contain anything even slightly secret. Right, where were we? Yes. So when this says up, comma, left, that means move from this arrow here to this arrow here. This processor, on the other hand, moves from this arrow here to the accumulator, then subtracts the thing that comes in from the right, and then moves the result to down, moves the result from the accumulator to down. This processor just repeatedly moves from up to down. This processor moves from up to accumulator and then sends that both to right and to down. And this one moves 0 into the accumulator, subtracts the thing that it receives from the left, and sends the result to down. So it negates it. Is that clear, kind of? So you can see left processor moves up to accumulator. The right one stalled because it can't execute that mov up left until the processor on the left, or rather it can't finish that mov up left until this processor reads that 93. Then it reads it, which means that this processor can start running again. This one has then done that subtraction and come out with minus 49. That then gets sent down through this pipeline here. Meanwhile, these ones are doing the next set of sums. But let's follow this minus 49. It ends up in the accumulator of this processor, gets sent to the right, and thus this one, which has already initialized its accumulator to 0, can then subtract that, getting plus 49. And meanwhile, this processor sends that minus 49 out there, and this processor sends 49 out there, and we passed the first one of the tests. Hooray! And meanwhile, you can see that the pipeline is a couple of steps ahead. There's the next one, which is 18 and minus 18, and they're currently working on the next one, which is going to be 4. And so then I can hit run and let the rest of the program complete. And so, yes, the general point of this is that, as Claire says, you can be working on lots of different bits of the problem at the same time. As Ian said, the slight problem is that no one is actually any good at programming these. Yes, Jacob, this style of programming does feel like a marble machine.
Definitely something.
And it is quite fun when it all works. So, I mean, so what a horrible layout of processors. So, for a message from Randy in September 1979. So he must have acquired this when it was fairly new, because the copyright dates were like up to 75 or so, weren't they? Found a block of static memory, but it's in a proprietary format I never saw before. Can't make heads or tails of it. Oh, brother, there's just too many different kinds of machines coming out now, and I like tinkering with them as much as the next guy, but when every Tom, Dick and Harry implements their own memory address scheme, it's all disaster. I say the bottom's going to drop out of the microcomputer market soon. Mark my words, he says in 1979.
Yeah. One of the Apple II, flower, fish, hamster.
So, this is when the programs start to get tricky, as I recall. Read a value from in. Thank you, Dr. Swirly. Read a value from in. Write 1 to out. So in is up here. Write 1 to out.g if in is greater than 0. Write 1 to out.e if in is equal to 0. Write 1 to out.l if it is less than 0. When a 1 is not written to an output, write a 0 instead. So, and the slight awkwardness here is that we have a great big slick of broken processors in the middle. So we have to do this like by working our way around the edge a bit. But this shouldn't be too hard, actually. Surely what I do is I pass all of the input numbers along here, and each of these processors processes them as they go past. So we do the fairly tedious bit of no, that's not going to help. Move up. Right. There is no down port on that processor. So G, if the number is greater than 0. So this is actually fairly simple, isn't it? This is teaching you how to do conditional things. So in Shenzhen IO, the processors had dedicated compare instructions that set condition codes, and that you could then effectively inspect those condition codes in any instruction. I'm wondering if this doesn't actually need the commas. I never wrote the commas in Shenzhen IO, but the manual has commas in, so obviously they canonically have commas. So yes, Shenzhen IO processors had condition codes that were set by special compare instructions, and then any instruction could be conditionalized on them. The TIS-100 goes in pretty much the opposite direction, in that there are no special compare instructions. Instead, there are conditional branch instructions that only pay attention to the current contents of the accumulator. So this is, I think, actually a bit nicer to code for, because you can often do more fun things with it. You don't spend all your time going, oh gods, what have I got in the condition codes? Yes, it strictly means we have fewer registers, but it doesn't seem to be too much of a problem. So we have, in particular, jump if equal to 0, jump if not 0, jump if greater than 0, jump if less than 0.
Grump if less than 0.
And my favourite instruction, JRO, jump to, or essentially add some source to the program counter. And there's also an unconditional jump. But in particular, I have written so many programs where a processor goes JRO left stuff, and thus you can have the next processor upstream of it feeding it a bunch of meta instructions. So essentially, then it actually becomes a microcodable processor. Kind of. But in this case, this is fairly simple. All we want to do is say, is the accumulator greater than 0? We have a JGZ, so we could go JGZ yes, morv naught down. Let's have a top label at the top. And at yes, morv 1 down. We should probably actually send the data onwards as well. Morv ac right. And then we want basically the same thing here, except that wants to be JEZ. And we kind of want the same thing here, except that we don't want to send it to the right, because there is no right. And I think that should do it. I think a small bat is saying hello. Right. And so that seems to work. Though it's kind of slow. And yes, there is a fast button, but still.
Doesn't that turn the display off, though?
No. Clearly there is a... yes, this is more or less the standard answer to this one. I kind of feel it ought to be possible to like, make that quicker, because there's an awful lot of instructions per byte going on here. Like, can we not do some of that processing earlier? But yeah, whatever. Let's keep heading onwards for now. Signal multiplexer, wherein Randy has might have an idea of where this TIS-100 machine came from. Described the architecture to Fred at Motorola, and he says, sounds like it was designed for signal processing. Yes, that got my brain going. Government project maybe? Something the CIA cooked up to comb through the Soviet radio channels? Hush hush top secret? Maybe. We've reached, incidentally, January 1980 now. Could I be in possession of a classified secret device for spooks? I might have to sit on this one for a little while. Yes. Well, I mean, you could write... Jacob says the real trick is to have a node count greater than 6. I mean, you could write utter rubbish in the spare nodes. Signal multiplexer. Read values from in.A and in.B. Read a value from in.S. Write in.A, presumably to out, when in.S is -1. Write in.B when in.S is +1. Write in.A plus in.B when in.S is 0. So, I mean, I can start using my favourite programming technique immediately. Why not? So, the foolish thing I think I'm going to do is start each of A and B with a JRO instruction that expects to receive from the middle processor an indication of what they should do. So then what the middle processor will do is something like mov up ACK actually, this is going to be kind of inconvenient, isn't it? We're now wondering if I can do something. No, we can't do something appropriately silly, sadly. Because JRO 0 is like halt. I was wondering if we could just pass on this number to either side and then write the code in such a way that it magically does the right thing, but I don't think I can. I'm now wondering if I build a tiny jump table. Thank you, Gareth.
A hop table.
A hop table, yes. Well, I mean, what if I, for instance, instead of that, went mov 2 ACK add up, oops, JRO ACK, and then it would jump to one of the next three instructions based on whether in.s was -1, 0 or +1. I mean, I'm not actually sure that's helpful though, so let's not do that. At least not initially. Let us instead do something fairly simple. So I'm going to end up calling my labels things like X and Y because coming up with names for them is tricky. So
Not just because of use to Shenzhen.io, which only lets you have one.
no, it allows you multi-character labels as well. Just the problem is if you make them too long, your instructions don't fit anymore. In particular, in Shenzhen.io, all instructions were by default indented by 2 spaces. So if you use single character labels, your labelled instructions end up at the same position as your unlabelled ones. And your only problem is a labelled conditional instruction. Here we have no condition codes, and therefore everything is unindented, so it doesn't matter so much. So if we are less than 0, then that means we don't want... So what my plan is here is that I'll instruct each of these processors to pass on either their own input or 0 to the next processor in the chain. And then something down here will add the 2 streams of numbers together. That's the idea. So this should read from... So yes, so this should then, if we reach here, we've said X, we've said the accumulator is less than or equal to 0. If it is less than or equal to 0, then we include A. If it is greater than 0, we do not include A. then we do the same thing in the other direction. So now I'm just going to write the same thing but backwards. Now 0 and 1 being written to each side are currently a bit arbitrary. W essentially means skip this last instruction, which may as well go back up to the top. So then this side will have two things it can do. One is mov up null mov naught. Is it called null? Is it? I was vaguely nil. That's better. Mov naught down. And the other one will be mov up down. And like here, I am totally demonstrating a trick that's mostly useful much later in the game, but it's fun. I don't think I've got the relevant word. Oh, I might have actually. I think Pink Beast is oh, I can't work out how to phrase it in English. Kangjong. The adverb meaning while jumping like a rabbit in Korean. Well, more or less. Right, Kangjong is probably closer. So those numbers actually want to be 1 for don't include. So and 1, 2, 3, 4 for include. Right, so that's a ludicrous piece of code. The idea is this reads in the selector and then either sends 4 or 1 left based on whether A should be included, and either sends 4 or 1 right depending on whether B should be included. And then these read those numbers and either absorb what comes in on the top and send out a 0, or just send what comes in from the top to the bottom. And then these two processors just funnel data into the middle one. The middle one reads data from the left processor and adds what comes in from the right and moves the result downwards. And this one just funnels data from up to down. And in a moderately shocking state of affairs, that piece of code worked first time. And so this, we can see from the idle figure here that this processor is the limiting factor. If we wanted to make this faster, and oh gods are we slow by comparison with some people's solutions, then we would probably want to, well, I mean, I think actually the right thing to do is to have the decisions made in these processors rather than having this one making all the decisions. So you could probably do much better by having this one just send what it reads out to both of these, and each of these do a conditional JGZ on one side and JLZ on the other side, and that would almost certainly be a much more sensible design. I think I should try that. So if we were to do that, let's keep the rest of the design, but instead have this one go like that, and then these get completely rewritten so that they instead go so A is included, or rather A is excluded when S is greater than 0. So this is only slightly more instructions in each of these processors and many fewer in the middle one. Obviously we have to change that right to left, and we have to change that JGZ to JLZ. That's faster. And we can now see that all three of these processors are running at pretty much 100% capacity. Yes, I can use the back register, but it's even more restricted than the back register in the Shenzhen IO processors.
Yes, I was just reading about that. Unlike
And yet more useful.
unlike DAT, you can't directly use it as a thing to add.
Yes.
To add. But on the other hand, you can swap.
Yes.
the two values
And swap
without
is
them.
brilliantly useful, and I missed it so much in Shenzhen IO because essentially without it you have
You
one
might
fewer
find
register.
storage somewhere.
Yes. Right, that's a rather more efficient version of that program. Still not the lowest instruction count that anyone's achieved, but it's a very fast version.
I do keep wondering about these triple graphs, whether they ought to be some kind of histogram in a three-dimensional space.
Yes.
I mean, when it says some people have managed this low in instruction count and some people have managed this low, this faster speed, and you go, yes, but has anyone managed both at once?
Yes.
And if they have, then you want to try. And if
But-
they haven't, then you don't want to waste your time trying.
But on the other hand, how are you going to draw your four-dimensional histogram?
Yes, well, I mean...
So you can do almost nothing. Basically, all that you have for back is, as I recall, the SAV instruction, which copies accumulator to back, and the swap instruction, which swaps the values of accumulator and back. And that's it. But this turns out to be much more useful. This turns out to be, in many respects, more useful than the DAT register in the Shenzhen IO processors. So it's reached 1994, which is like... Yeah, so he's basically wandered off from this thing for 14 years, discovered ISO 8601, the new girlfriend is encouraging me to get rid of the microcomputers I've accumulated over the years. Not a bad idea. Most of them are just taking up space and aren't doing me or her any good. Going to wait on this one, though. Never found what its whole deal was. And if it turns out to be something I wasn't supposed to have, I think I could get in trouble. Cleared a little space on the workbench and hooked it up. Still works. Beautiful. Yes, it is a beauty, this one. Right. So, yes, now things get entertaining. Sequences. Jutton says maybe he went on an ISO 8601 date with a new girlfriend. Bigby says he is not jumping like a rabbit in Korean.
Which suggests he's 7 minutes behind the stream.
So sequences are zero terminated. Read values from in.A and in.B, write the lesser value to out, write the greater value to out, then write a 0 to end the sequence. Right, so this is going to require at least some use. Well, it's going to require something like back. Whether we actually use back or not, I'm not sure. Probably we do, because notably there is no compare instruction on the TIS-100. If you want to compare two values, you have to subtract them, and then you've lost one of the you have in some sense lost one of the values. No, there's no slip instruction here either, because there is no time. Essentially, Shenzhen IO had two different kinds of time. TIS-100 only has one kind of time, which makes it a lot less confusing. So, I mean, probably the sensible design here puts most of the hard work in one processor, I think. And so it does something like mov up ACK, save a copy of that, sub left. So then in ACK we know which way around the two values should go by whether ACK is positive or negative. If it's 0, it doesn't matter because they're equal. None of the test cases I can see there has... Oh no, there's 79 and 79, which you have to output both of. I think processors... Well, I noticed that there are arrows pointing into the dead processor, but no arrows pointing out of it. Maybe I should try feeding some data into a dead processor and see what happens.
I mean, if there's mysterious stuff hidden in the microcode, then who knows? Maybe they will...
Looks like it just jams, I think, because it's stuck in writing to the left processor. So yes.
He likes jam.
So I think while they are connected, they will just seize up as soon as you try to write to them. So that... So that's the kind of structure of the actually doing the comparison. And then we want to write them out in one order or the other. So let's do the usual thing of sticking a label saying T at the top to jump back to. So if we are greater than 0 after subtracting A from B, then that means that B was greater, and so we want to write A first. So then we should do mov left down swoop mov ACK down. Alternatively, jump T. No, my T is finished. Yes, the debug button is the thing, as Jutton says, for reading the note. It's called Randy, not Jeff. Has written in the scribbled in the microcode space. So yes, I suspect that compute node did once work, and then Uncle Randy scrawled all over its microcode, and now it's broken. But like, it looks like it uses a different cluster of processors for each of these tests. So happily, there are plenty of processors sprawling the microcode space off. So it's not like this is actually only a 12 processor machine. It's like it's got 12 processors for each of those 25 tests, and then some. Right. So, and then in this case, we want to do things the other way round. So we go swoop, mov, ack, down, mov, left, down. So this processor is expecting to receive each number twice, once to do the subtraction and once to actually send it to the output. Oh, no, don't. Well, we do have one other thing we have to do, of course, which is mov 0 down, mark the end of the sequence. So this one needs to go mov up ack, mov ack left, mov ack left. And then the usual thing where we've got slightly too many processors, so we just have to have a few of them shuffle data around. So we've got, this one is going to be our rate limiting step by quite some way. Let's see what it does. Oh dear, doesn't work. Because I'm an idiot. Left from that processor isn't going to work at all. Right will work a lot better. Oh, it goes buzzed when you get it wrong. I didn't know that. I've mostly played this without sound. Okay, I've got everything precisely backwards, haven't I? Right, let's just change that JGZ into a JLZ. No, I don't always program like this. Well, I mean, it's a bit slower than most, but on the other hand, I've used fewer instructions than most. It'll do. Segment 31,904, sequence counter. We're getting into a rather nice normal distribution of cycle counts there, aren't we? Oh dear. No, she won't understand. Of course she doesn't. Why would you expect her to? Well, she might. Just keep working. I feel like I'm learning. Sorry, yes. No, she won't understand. Of course she doesn't. Why would you expect her to? We're in 1994, which I think was where we were before. Just keep working. I feel like I'm learning about the people behind this and their design decisions. The thoughts that went into figuring out how things should work. Those people feel very close to me now. So now wondering if I have a video filter I can apply to turn everything black and white. Certainly do. At least I've got lots of other things. Apply lookup table. But then I have to add a file which is the lookup table. That looks like it's going to be more effort than I can be bothered with right now. What does a colour correction filter look like? Ooh! Right. There you go. Now my communication failures are bright green. Is that any more readable? Anyway, right. Okay, well, I shall leave the colours corrected to ludicrous bright green. I just opened the colour correction filter and dragged the hue correction slider from 0 degrees to whatever, and until it came out bright green. Right, so... Sequence counter. Sequence is 0 terminated. Read a sequence from in, write the sum to out.s, write the length to out.l. So we have an out.s here, an out.l here. So the obvious thing to do is to have one processor that's responsible for sums and one that's responsible for counts. I can see both, but yes, if there were any green, it would come out as something else again. Because I've got my actual TIS-100 window, which has a kind of dark red. Sorry, and somewhere over here, which you can't see, I've got my my OBS window in which I can see that you're seeing it in green. Because unlike Shenzhen IO, TIS-100 has a lower native resolution than my screen does. It has a bloody stupid resolution. Well, it has a perfectly sensible resolution, which is the resolution my old laptop screen was. But it's not the resolution that either I was streaming Dwarf Fortress at or that I was streaming Shenzhen IO at. So, what are we doing? Yes, we're devising two processors. Let's just do some plumbing. So I think we can now, this processor will handle sorting out the sum of a list. I'm now slightly worried. Let's do the length first, because that should probably be easy. Should it? I'm just thinking what's the right way to do this. Because we're meant to detect when we reach the end of the list, but that means that the accumulator can't just contain the length of the list all the time, because we can't check whether we've reached the end of the list without putting something in the accumulator so that we can do a conditional jump on it. Which makes me think that my traditional stupid trick of having one processor issue instructions to the next one might actually be a good one here. So we could have this processor, for instance, alternately take essentially opcodes and optionally the next item in the list. So we would have something that went something like this: a JRO up, and then a first target which would be output the accumulator, 0 the accumulator, and a second target which would be actually just add 1. And then basically the same program here. No, you can't do middle button paste, that's too optimistic, except that that becomes add up. And then, actually, let's be slightly weird and make that mov up nil. so now I'm going to undo some of my plumbing. No, I'm not. I'm just going to change this processor to generate a new form of sequence. So what it will do is mov up ACK and if it's 0, go somewhere else. So if ACK is not 0, it will mov 1, 2, 3, 4 to down, and then mov ACK down, and then jump back to the top. If ACK is 0, it will mov 1 down, and implicitly jump back to the top. Right. So this is a silly design, but it looks like it kind of will work. So, so my problem was that that if I want to, that I'm meant to be looking out for zeros in my input and doing something special when I find them, and at the same time counting either the number of values, non-zero values that I've seen, or adding together all of the values that I've seen. And both the checking for zeroness and the adding things require the accumulator, and they require the accumulator for different things. So one approach would have been to muck around with back, but I thought a more entertaining approach would be to take advantage of the fact that I've got lots of processors. And so what this processor does is it takes a sequence like 1, 2, 3, 4, 0 and replaces it with 4, 1, 4, 2, 4, 3, 4, 4, 1. So any number that isn't 0 gets replaced with 4 followed by itself, and zeros get replaced with 1. As Diziet says, who needs registers when you have comms channels? Yes. I have resorted in this to processors that just do mov write and use them as one-shot registers. They work quite well. Or mov left if they're on the other side of the board. These two are just plumbing to connect that stream of events down to both of these, and then each of these takes the first instruction and uses that to decide whether to uses that to decide whether to write out what it has so far accumulated and zero it. That should not say mov naught down, that should say mov naught ACK. Whether to write it out to downwards and zero it, or whether to add or count it instead. So that might work. So let's just slightly watch it single stepping for a bit. So you can see we're going to receive 35 followed by 0, and we should thus write out 435 1 from this processor downwards. Which then runs down into this processor, and you can see it jump to that add. There goes the 35. And there's the 1. And so they output 35 and 1. That looks good. And so while a comprehensively silly piece of programming, this does more or less appear to work. So rather curiously, this is the processor that's got the least idle time.
which feels kind of strange. But look at that instruction count. Slightly slow, but we did it with only 5 nodes and we only needed 21 instructions because slight silliness. I mean, also it's a really sensible design for these processors. So, yes, I like that. Right. See, things are starting to get tricky now. Let's debug the communication failure. 1994 dash bleh. Days and days and days and days, cycles and cycles and cycles and cycles. Just one after another. I'm sick and tired of people who don't respect me. Time to pack it up. Meanwhile, can we make this go? Signal edge detector. Read a value from in. Compare value to previous value. Write 1 if changed by 10 or more. If not true, if not changed by 10 or more, write 0 instead. The first output is always 0. I notice our first input is 0 as well, which might be helpful. I'm not sure if we can rely on that. So, I mean, we don't need to keep the value. So it feels to me like mostly we're going to do repeatedly sub up and then see if what we've got is outside of the range minus 10 to plus 10. Minus 9 to plus 9 inclusive. So can we do that within one register? Yes, we can. So at this point in the program, yes, thank you, Dizzyit, you are quite correct. Dizzyit says, but then you won't know the value to compare against next time. So I won't, yes. Okay, thank you. Well, we could use back for this. Though, as Dizzyit has said before, who needs registers when you have communication channels? So, I mean, we could go... yeah, that would work, wouldn't it? Dizzyit says, how about a number doubler? So, morv, by that I think they mean morv up, ac, morv, ac, down, morv, ac, down. And then we can just... I think it actually turns out that we want that we want to do something slightly bizarre with that to get the timings right, but because actually we want it to, well, I mean, what I want to be able to write here is something, I suppose we can just write this in a different order, can't we? Yes. So we could do sub-ac stuff, morv up ac. And then that will then mean that we reinitialize things each time. Yeah, that'll work nicely. So, good evening, Steph. Assuming you're on, you may not be watching this. Indeed, you probably aren't, and that might be for the best. Because if your head is all weird, this will not help. So, so if we go add 9, Send the subtracted value to another CPU to avoid branching in this one. I think I'm going to write what I want to write because I don't think I can handle working out what Dizzyat's trying to achieve. Dizzyat, not that I wish to stop you from making suggestions, but I will occasionally ignore them because I don't understand them. And trying to understand them is not what I want here. So please continue to make suggestions. If you want your suggestions competently executed, I recommend buying a copy of this. So my idea is that we have this. So if after we've added 9 it's changed by 10 or more, then after we've added, so if it were minus 10, adding 9 would still make it minus 1, which is what we want. So if it's less than 0, that's a large change. So we'll have that jump to a label called L. Then we can go sub 18, 19. Oops, probably shouldn't do that on stream. Then sub 18. So that would then mean that if we'd started off with plus 10, it would then have become plus 19. And then we subtract 18, it becomes 1. That's good as well. JGZL. So then L becomes mov 1 down. Have E for the end. And if we don't jump to there, then we mov 0 down. And that has to then have a jump E. I'm kind of wondering if there's a cleverer way to do this, but that will probably do. So the first output should always be 0. Good. Oh, we could do with like writing some code in the last two processors, couldn't we? Right. I mean, while there aren't that many people I would genuinely recommend this program to, actually, most of the people on the stream now are among those that I would. Like, I'm pretty sure that Dizzyat would find this quite fun. And probably Jacob, and I wouldn't be surprised at Steph or Seb either. Well, that wasn't very good, was it? What went wrong there? So the first cycle went fine, it sent a 0. So the second cycle, we receive 32. So we should subtract that. Okay, that's... I've got my cycles wrong because we received a second copy of that initial 1. That initial 0. So our problem is that we actually need, we really only want to see that initial 0 once. But if we're going to, do we want to see it -1? No, what do you mean by that? What do you even mean by that, Harris? So at the moment, how many times do we? So we see the 0 there, which is fine. But then we get we copy it then to there. Why do we end up? Oh yes, hang on. So what I want is yeah, I'm sorry, Dizzy's comment, I can debug programs anytime I like. I don't have to buy a game specially. I seem to remember seeing reviews of this that seem to split roughly into, oh my god, this is just like my work, I really hate it. And wow, this is really fun. It's like programming but without all the annoying bits. Or rather with a completely different set of annoying bits, which is my kind of attitude to it. Like, this is all the kinds of bits of programming that I don't get to do anymore. Anyway. Where were we? Yes. I was going, we've got an awkward synchronization problem where... What does this... Let me actually think about what this processor expects to receive and whether we can adjust things so that it expects what it actually receives. So it expects to receive, in order for it to do this right, it needs to, its first out, it kind of knows that the basic value is 0, and it then expects to read that one once in order to subtract it, read it again in order to make it the base, and then it should the next time read 32, subtract that, and good things will happen. Okay, I think this is correct. Right, why does this not work? So it receives... Hang on. What are you on, you idiot? No wonder it doesn't work. Subtract up. Okay, why is this processor running away before that one sent it any data? Because it's not actually reading. Right, there we go. That's better. Right, now my program works properly. Of course, I'm now going, well, is the test case generator making sure to look at, to especially target the areas around the precise boundary conditions? It probably is. My one for the Daisy Wheel printer tried to do that. It had a special logarithmic distribution of test cases. Right, well, that was a pretty good solution. I mean, cycle count a bit high. I suppose that's might be kind of flappy. So if we run it, that one is, thank you, is over here being kind of flappy. That one is certainly the one that has the lowest idle time. Though there's clearly a bit of general inefficiency. I suppose the fact that we do, yes, those two instructions. Ooh. No, that's going to be quite hard. I mean, we could probably make it, so we could probably make the cycle count lower at the expense of slightly more instructions by using using a delay slot. So the problem is that that instruction and that instruction come immediately next to one another on this processor, but they're separated by that mov up ACK on this processor. So this one ends up stalled for that one instruction. But if we could arrange that this mov up ACK happened earlier, then we wouldn't have that problem. So if we took that instruction and put 2 copies of it there and there, and then move that label up to the top, then we should get something in which this processor is much less idle and the whole thing has a rather lower total cycle count. And I've forgotten what our cycle count was for the previous version. There. Well, we'll see how we look on the... So that's got our cycle count down to closer to the modal cycle count, while still keeping our instructions pretty low. So Steph asks, are the in and out locations fixed? It seems kind of inefficient that you have to shuffle data right down at the end. Yes, the in and out locations are fixed. We can't change that, I'm afraid. Segment 33762. Thank you. Interrupt handler. From Compute Node Diagnostic Microcode Dump, 1994, 12:30. My sister was over for the holidays, I think to check on me, make sure I haven't gone off the deep end. This is this, I wonder, the person we got the note from? I know I caused some worry. Her kids saw me working here and suggested I could surf the web for TIS-100 specs. So even kids are on about internet, online, blah, blah, blah. It's a racket. I don't care about the information superhighway, and I never will. Interrupt handler. Read from in.1 through in.4. Write the input number when the value goes from 0 to 1. 2 interrupts will never change in the same input cycle. So, and implicitly, though we're not actually told that in the spec, write to 0 if none of the inputs has changed. Well, I mean, to me, the obvious approach here goes something like... what does it go like? I mean, my kind of high-level approach is blah, 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 mov, naught, right, oops, or mov 1 right, depending. And then this one goes blah, 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 mov left, right, put the commas in, Ben. The manual says you should have commas. Blah, 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 or mov 2 right. And this one goes the same thing. Or, and then this one though I am now wondering if we should do this with many more processors to allow the priority encoding to be done on this layer and the edge detection to be done on this layer. But I think that's extravagant. So now we just need to work out what the conditions are for these. I mean, actually, we can finish writing these, can't we? So then the idea is, actually we probably don't need x, but still, that we basically jump to x or y depending on whether we do or do not, or do not or do strictly want to signal an interrupt from this port. Right, so now how do we actually code this? So we want to note when we go from 0 to 1. So one approach... So I can see two approaches to this. One is that we have a loop that we sit in when the input is 0 and a loop that we sit in when the input is 1. And we transition between these loops when the input changes. And the other approach involves storing what the input currently is in a register. And it feels to me like the first one of those is going to be much simpler, because otherwise we're trying to do arithmetic on, and we can do it, I think, but it's kind of painful. So let's go for storing the current state in essentially the program counter. So in that case, we don't actually, well, we do mov up ACK, but thus, actually, so we have a little loop up here that does essentially if the input has gone up, then jump somewhere else. Otherwise, signal no interrupt and jump back to the top. If the signal has gone high, let's make that Y. Oops. If the signal does go high, then signal that interrupt, continue reading from the accumulator, we don't, whatever happens, we can't send an interrupt while the signal is still high. But if it's low, jump back to the top. Otherwise, stay in the high loop. I'm missing a bit of code here. Mov up, so that's... no, I'm not. Right, I think that's actually correct. And so now I want to do basically the same thing in all of them, except that mov 0 right will become mov left. Hang on, that line of code there does nothing at all, as does that one. Let's remove those. They're unreachable. And that becomes MOV 2 right, and that becomes MOV left right. That means no one's going to hear the sound anymore.
Really?
They can hear me, but they can't hear the things going beep anymore.
Oh, sorry.
No, it's fine. It's fine.
Oh,
I'll
sorry.
just turn on a different speaker.
Sorry, I thought it was being helpful. Hello, stream. I was being helpful, but stay.
Right, so this one then wants to do the same thing, but MOV 3 right. And this one is pretty similar, except that becomes a 4 and all of the rights become downs.
I would stand here and go beat for you, but I'm going to snooze. Good snooze screen.
Comma. 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 Right, down. I think the beeps will still work, but we'll find out in a bit. Actually, I can press this, can't I? Yeah, that's some noise at least. I mean, you're getting it through my terrible laptop speakers and then back in through my fairly terrible laptop microphone. Right. And then some slightly silly plumbing because Jutton asks, Diziat asks, don't you need to eat the ignored values from the upstreams? You're right, I think I do. Because where this does MOV left right, obviously if it doesn't MOV left right, it needs to do something with whatever turns up from left. As you can see, I am confused by the register naming on this. Got it right in that one. Right, okay, how about that then? Does that look better? I think it does. Though I have to say that MOV up ACK is kind of pointless when we don't pay any attention to what we what we do with it. What we do to the value we end up with there. We could just have that be a MOV up nil as well. But the writing to the accumulator doesn't cost us anything. So, bets on whether this works. Looks good. Now, the pleasing thing is that I'm already going, I have no idea how I solved this one last time. I'm fairly sure I didn't write that. So, yeah, that was a pretty good solution then. Other people seem to need at least 9 nodes to solve this. And yes, kind of interesting distribution there. So apparently there are some more efficient solutions in terms of instructions. I kind of suspect it would be possible to, I mean, that node is clear. The minimum number of nodes is obviously 6, because you simply can't connect everything with fewer than 6 nodes. And that one is obviously doing something a bit silly. You could easily have that job be done by this node with a bit of faffage. Dizzy, it says swapping some branches would delete 4 instructions at the end of each program. Probably, yes. So yes, we've got a JEZT jump H, which could be a JGZH, couldn't it? That doesn't even require a serious redesign. It'll make it slightly faster. Shame you can't have a macro-based thingy for this copy and paste. Well, yes, obviously having some kind of horrible macro assembler would be more in keeping than like actually having working copy and paste. Right, so now our instruction count is more or less minimal. Our cycle count is more or less minimal, and our node count isn't minimal because people have done it in 6 nodes. But with 6 nodes, all the symmetry would go wrong. Like, yes, saving that jump because the wrapping round jump doesn't cost us a cycle. It ends up going faster as well. So yes, in theory we could dispose of this processor, but that would add so much weirdness across these two that I don't think I'm going to do it. I think I'm going to see what we have next. 11:30. So the next segment is actually, would you like to write your own program doing absolutely anything at all? We've written a thing that counts. I'm not going to attempt to implement Simon in this. For one thing, it has no input. Oh, it does have a console input as well. Oh, gods. Does that just mean I can type in arbitrary numbers? Yes. Right, I don't think I've ever played with the console before. I'm not sure I have any idea what one might do with it. So let us leave the sandbox for now. I think what is this next one then? Okay, no, let's do this one. I'm kind of going, if we reach the stack memory ones, I should probably stop. But 2004, so we're now another 10 years on. The noise from the garage, but it turns out nothing. So now that I have plenty of free time, I might as well get back to this. Keep my skills sharp while I look for a new job. I'm not sure actually programming a machine from the 1970s is going to keep any relevant skills sharp. I appreciate you might wish. Sorry, IRC has just included the line, I say, my dog's got 9 vertices and 36 edges. Which I'm not going to try to work out what the correct answer to is to. Oh, God. Thank you, Dr. Swirly. So possibly my idea of how does it embed in the plane was probably correct. Anyway. Right, yes. Read a value for in, look for the pattern 0, 0, 0, write 1 when the pattern is found. If not true, write 0 instead. Dizzy, it says, BJH21, can you parse XML with this thing? Well, I mean, we're starting to write a parser here, aren't we? You know, except for the fact that it is well known that you can't parse XML with regular expressions. And actually, or rather, you can't parse HTML with regular expressions, but I'm pretty sure it extends to XML. I'm fairly sure we could do some kind of a finite automaton here. I think I'd start with JSON rather than XML. Also, it only reads and writes numbers. Though you will observe that it reads and writes numbers up to 999, which is another way it's similar to the processors in Shenzhen.io. So, I think I can remember how I did this one. And the problem is that the way that I did it is very cute, and I want to do it again. Though I'm thinking there are other interesting approaches. Like, I'm fairly sure... Actually, let's try to do it a different way. So I think the way that I did it last time was a very spatial one, in that I, sent my input stream down through all three of these processors and arranged that we, detected when we had a 0 in this one, and a 0 in this one, and a 0 in this one. And then sent a signal down here saying, found one. But I think there is an alternative approach involving my favourite instruction. Of having two things that you can do based on an input signal, one of which is mov 0 ac. And the other one of which is add one, no, sorry. We now want the minus condition code, because I actually want to go mov -2 ac. Because then we can go add 1 JEZ. Maybe I want -3. If we're going to do it in that order, yes. I'm going to... This is all slightly confused, and I need to redesign it. But when you see 0, 0, 0, they mean when the last three at least things were 0. So let's go JGZ. So then the idea is that when we get non-zero, when we receive a non-zero value, we'll write a thing in here that handles converting 0 and non-zero values in a bit into A and B. Dizzy says no test case will be a sequence of 1,000 zeros, right? First, no, because the test cases can only be this long. Second, I think this shares with the Shenzhen.io processors that it has saturating arithmetic. Though it may not be documented. I'm just going to look through the... All registers store integer values between -999 and plus 999 inclusive. The representation of register values is implementation defined, and knowledge of the representation is not required. There doesn't seem to be any specification of whether the arithmetic saturates, but I think it does. Anyway, so I think this will work even if we have more than 1,000 zeros in a row. So if we receive... So we'll arrange that we jump to A if we receive non-zero, which means we set the accumulator to -2 and then read the next value. That's not right. Set the accumulator to -2, send 0 downwards, and go. So what I mean by saturating arithmetic is where if you try to do arithmetic that would overflow, you instead just get the maximum possible value. So, for instance, here, the largest value you can store in a register is 999. If you attempt to add 1 to a register that contains 999, then it stays at 999, rather than either becoming 1,000, which it can't, or wrapping back round to -999, which is what most processors do, though GPUs in particular tend to have the ability to do saturating arithmetic instead, because if you're dealing in things like pixel values, you would much prefer them to saturate than to wrap around. And similarly, if you're dealing in floating point, well, it's quite hard to add 1 indefinitely because things just start ending up being constant, but they do essentially the same thing. No matter how much you add to a floating point number, it will never become surprisingly negative. And this can be quite helpful, and Simon and I have been whittering about saturating arithmetic for memory allocation in puzzles recently. Because, we would quite like, when you multiply the width and the height of a puzzle, for you not to bizarrely end up with a negative number. So, where was I? Yes. So, if we get non-zero, we intend to run this bit, which will reset our accumulator to -2, say we are not currently haven't seen a sequence of 3 zeros, and jump back to the top. If we do see a 0, we add 1 to our accumulator, and if it's then greater than 0, i.e. we've seen at least 3 zeros, then we jump down to here, write a 1, jump back to the top. Otherwise, we write a 0 and jump back to the top. And it kind of feels to me that we can probably do a better job of this by flipping some signs around and having that instead jump back up to that convenient MOV 0 down. If we make this JLZ N and then make that N, and then have this start at -3, then we can remove those 2 instructions. N colon. Right. So then we can stick these in. And then our only problem is this bit, which I've kind of left out, which wants... So what this wants to do is say, if its input is non-zero, it should write 1 to its right-hand port. And if its input is 0, it should write 1, 2, 3, 4 to its right-hand port. Right, that's fairly simple. So, should we single step this one? I think we probably should. In particular, it would be helpful if those 2 bits of code agreed with one another. So that writes 1 because it was non-zero, which means it goes to there, keeps ACK at -2, sends a 0, goes back to the top. Then receives a 4, which jumps it over to there. Okay, I think I've got my ranges wrong because, yes, that did the wrong thing. I think that should have been -3 at the very least. At the very most. Right, that's looking better. And there we have it. Yes, the single stepping does go clack, doesn't it? That went boop, but also blobble. Fairly sure computers aren't meant to go blobble. Let's test that again. Wonder if it always does that. Good night, Steph. Yes, definitely went blobble that time. Fairly sure the previous levels didn't go blobble. As I said, I haven't played this with sound before. Right, well, that was a fairly efficient solution then. Like, other people have got lower cycle counts, but almost everyone does it in 4 nodes. And we did a pretty good job of... Yeah, so there was a noise behind the beeping noise. There was a kind of slightly liquid noise. Which I don't think the previous one had. Okay, maybe it did. Right, I'm going... Is this next one really annoying and difficult, and can I do it in 20 minutes? I mean, I don't really want to take 20 minutes, because I'd like to get to bed before midnight, in theory at least. So I think actually I should not attempt the next one now. And instead I should save this, and if there is desire for me to do more of it on next Sunday, then maybe we can do another batch. And I've kind of sorted things out for streaming at this weird resolution, so I think that will be fine. So yes, I think it's turning out slightly more entertaining than I was expecting. I think not helped by the fact that I have a pretty solid idea what I'm doing, at least in terms of how to program this thing. So I'm not... It's actually a bit different from Shenzhen IO. I don't have to engage my brain quite as hard, though it gets more difficult. Histograms, that one's quite an entertaining one. Plus, like, there's an entire... load of extra levels that you can't yet see here. Anyway, so I think I've got a good night slide on here. So I think that's all for tonight, and we will see you. Well, if there's more TIS-100, it will probably be next weekend, maybe on Sunday, possibly on Friday. Meanwhile, have a nice week. Good night all.